Welcome back. In the last couple of lectures, we have discussed that similarity requires that not only the total forces on the prototype and the model elements need to be scaled by a unique factor which depends on the scale factors of the mass and acceleration, but the same factor must scale every component force that make up the total force vectorially. So, for this, we identify the various force components that determine the net force at a point in the flow field, obtain the scale factors for each of these force components using the physical laws that govern the phenomena, and obtain the non-dimensional pi numbers in terms of the characteristic independent quantities from the relations established in step above. These give the invariants that establish the modeling rules. For example, let's look at the viscous forces. The shear force is shear stress into area. The shear stress tau is mu times the velocity gradient, and so k tau, where tau stands for shear stress, is equal to k mu times kv by kl. The area scale factor Ka is KL square as was shown in the last class, and therefore K for the viscous force is equal to K mu Kv times KL. This is the scale factor for the viscous forces. Similarly, we do for the inertia force. Inertia force is mass times acceleration. The mass is density times the volume. So K mass is K density times K length cubed, since the volume is like length cubed, and the acceleration from the convective acceleration we obtain, K acceleration, is Kv square divided by Kl. This was all done in the last class. From this, we obtain Kf inertial is K rho Kv square Kl square. And from this, I get the pi number Fi divided by rho V square L square. Now, the two scale factors must be equal. We'll apply this to an example. A 1/6 scale model of an automobile is to be tested in a wind tunnel at a speed corresponding to the prototype speed of 60 kilometers per hour. Determine the model speed required for similitude. If the drag on the model at that speed is 510 Newton, what is the drag expected on the prototype, and what is the power requirement of the prototype? In this case of an automobile moving on the road or as tested in a wind tunnel, the only forces of importance are the inertial and the viscous forces, and they need to be modeled. As we have just seen, Kf mu, the viscous force scale factor, is K mu Kv Kl, and the inertial force scale factor is K rho Kv square Kl square, just obtained. The two scale factors must be same, and from this we get K rho Kv Kl divided by K mu is equal to 1. Or from this we can obtain rho Vl by mu as a pi number. The modeling requirement is that the value of this pi number for the model should be the same as for the prototype. Thus, we equate the value of this pi number for the model and the prototype to obtain the velocity for the model. Rho and mu for the model and prototype are identical, and so V for the model is V for the prototype times L of the prototype divided by Lm. L for the prototype divided by Lm is the length scale factor, which was given as 6. And since the prototype speed is 60 kmph, the model speed should be 360 kmph. So model should be tested at a wind speed of 360 kilometers per hour, a rather high speed. It shall be seen later that the viscous forces are not very important in these cases. When the Reynolds number are very high and the body is blunt or bluff, as an automobile is typically, the viscous forces are not very important for drag modeling. And the fairly good results can be obtained by testing the model at almost any speed. Anyway, we'll come to that a little later. For the time being, let's predict the drag. The prediction rule for the drag is obtained from the corresponding scale factor relation. The scale factor for drag would be same as scale factor of any other force. And as we have seen, for the inertial force, the scale factor is k rho kl square kv square. So the scale factor of force is 1 into 6 square kl square into 60 by 360 whole square, which is the square of the velocity scale factor, and that turns out to be 1. Thus, the prototype drag will also be 510 Newton, the drag on the model, because the scale factor forces is 1. The power requirement to overcome the wind drag can be obtained directly from the velocity and drag, as power is the drag 510 Newton into velocity 60 kmph, and converting kmph to meters per second, we get the power requirement as 8.5 kilowatt. In this case, the prediction rule for power is not relevant since the model power consumption has not been specified. However, if it were somehow known, the prediction rule can be obtained from the power scale factor kW dot is equal to k rho kl square kV cubed. Let's do another example where Strouhal number and Euler number matching is to be done. This is related to a pump which is taking water from a water sump and pumping it to an overhead water tank. The pressure through this pipe is subatmospheric because pressure here is atmospheric. So pressure through this pipe is subatmospheric. There is jump in pressure at the pump, and then the pressure reduces further, and at the exit the pressure is atmospheric again. A pump capable of lifting 5 meter cube per second of water against a head of 250 meters, that this head, total head from here to here, is 250 meters, and the pump is running at 500 RPM. Before designing this pump, we need to make a model and test it. A 1/9 scale model, KL is equal to 9. Length of the prototype divided by length of the model is 9. A 1/9 scale model is constructed and tested with the same fluid against a 10 meter head. So instead of 250 meter head, we deliver against a 10 meter head. At what speed should it run? And what should be the volume flow rate if there has to be similarity? What would be the power scale factor? These are the questions that need to be answered. The pressure and the inertial forces are the only forces that one need to model in this problem. Since the pump is a rotary machine, centrifugal inertial forces should also be modeled. We organize our calculation in this manner. The governing law for inertia is inertial force is equal to ma, and we plug in the scale factors of mass and acceleration to obtain the scale factor for inertial force as k rho kl cubed for mass, and for acceleration kv square divided by kl. The pressure forces would be pressure times the area. So the scale factor of pressure force would be Kp, the scale factor of pressure, times that of area, which is KL square. Matching these two, this should be equal to this, and that gives us Kp is equal to K rho times Kv square. From this, we get the pi number P divided by rho V square, which was shown to be 1 over Euler number in the last class. The centrifugal force F omega is mass times omega square r, the radius, that's a length. And so the scale factor for the centrifugal force is K rho Km omega square into KL raised to power 4. 3 L's from mass and 1 L here. So KL raised to power 4. From this and this, we obtain similarity rule. K omega into KL should be KV, which gives us omega L by V, which is named Strouhal number and denoted by ST, Strouhal number. Thus, the similarity requires that the Euler number and Strouhal number must match. The Euler number similarity gives P divided by rho V square for the prototype should be same as that for the model. And from this, we obtain Kv is equal to rho m by rho p into under root Pm by Pp. Rho m by rho p is 1 since we are using the same fluid, so then density is same. And the pressure developed in model and pressure developed in prototype are 250 meters divided by 10 meters. So this gives you a scale factor for velocity to be 5. Then we use Strouhal number similarity, and from this we get omega L by V for the model is same as that for the prototype. And so omega for the model is obtained as 9 by 5, the value for the prototype. Since the RPM of the prototype is 500, the RPM of the model should be 9 into 500 divided by 5. That is 900. The model pump should run at 900 RPM as against the prototype pump, which is to run only at 500 RPM. The prediction rule for the discharge is now obtained by the scale factor for discharge. The discharge is like velocity times the area of the pipe, and so kq dot would be kl square for the area and kv for the velocity of the fluid through the pipe. KL is 9 and kV has been determined to be 5. So the scale factor for the discharge is 405. The prototype pump would discharge 405 times the discharge of the model pump. And since the prototype pump is to discharge at 5 meter cube per second, the discharge in the model would be measly 0.0123 meter cube per second. The scale factor for power consumption is kW dot, the power is force times the velocity. So kW dot is equal to kF times kV. And we use k rho, kl square, kv square for kf, the inertial force factor. All forces are same. So this gives you a power scale factor of 10,125. So the prototype will consume more than 10,000 times the power used by the model pump. I hope you appreciate the ease with which you can make the prediction rules based on simple relations of scale factors. Let's do another example, an interesting example of biological similarity. It has been claimed that various organisms and physiological mechanisms operate similarly and are governed by the same laws in different species. Therefore, various species may be treated as scale models of the same machine, and that the various biological functions must be scaled following the rules of similarity as developed here. An example, let's consider the Lilliputians and the Brobdingnagians of the Gulliver's Travels fame, who differed in the height ratio by approximately 1:150. Actually, the ratio was 1:144, because it was mentioned in Gulliver's Travel that an inch of Gulliver was a foot for the Lilliputians, and a foot of Gulliver was an inch for Brobdingnagians. Let us estimate using biological scalings their relative masses, frequencies of breathing, velocities of walking, and the maximum jumping heights. Which species would have more difficulty with the surface tension of water, with the viscosity of water, and with the Earth's gravitational field? So let's treat Lilliputians as the model, the smaller one, and Brobdingnagians as prototypes. The scale factor is taken as 144. The mass scale factor is simple. K rho is K density times K volume, that is K rho KL cubed, and so it's 1 into 144 cubed, 2.985 into 10 to the power 6. So giants would weigh about 3 million times the weight of the Lilliputians. To calculate the breathing frequencies, remember that the oxygen consumption per unit time is related to heat dissipation from the body. And the heat dissipation from the body depends upon the surface area of the body if the temperatures are the same. So, the oxygen required, the scale factor of oxygen required would be the same as the scale factor for the heat dissipated, which would be like the scale factor for area, and so this will be KL square. The oxygen intake per breath would be the scale factor for lung capacity, and which would be KL cubed, the volume. So the frequency of breathing, the scale factor for frequency of breathing would be the scale factor for the oxygen required divided by the scale factor for lung capacity, the volume breathed per breath. And so that turns out to be 1 over KL. So it would be 6.94 into 10 raised to the minus 3. The giants would breathe much slower, order of magnitude, 2 orders of magnitude, 3 orders of magnitude slower than the Lilliputians. Walking velocity, KL by KT, velocity is like length scale factor divided by time scale factor, and that is KL times KF, the frequency scale factor, and we have just seen that the frequency scale factor is like 1 over KL. And so the walking scale factor would be 1. The two species would walk at about the same speed. One taking longer strides but with far lower frequencies. To calculate the jumping height, we use a trick. We assume that the maximum stress level in all species are the same. Maximum stress level in the muscles. If the muscles do work, they exert force, and we assume that the maximum stress levels in all muscles, in all species, is the same, so that the maximum work done by the muscles in jumping is scaled by K work is K force into KL, and K force is like K sigma into KL square, so that K work is like K sigma into KL cubed. K sigma is 1, stress level being same, so the work done scale factor is like KL cubed. This work done is converted into a potential energy in a jump, and if capital H is the height jumped, K potential energy is equal to K mass times Kg, the acceleration due to gravity, times H. K mass into Kg into Kh. And for K mass, we put K rho times KL cubed, Kg and Kh. And for Kg is equal to 1, this is KL cubed, Kg, Kh. Equating this to K work, we get Kh is equal to 1, because Kg is also 1. So Kh would be 1. That is, the two species can jump up the same height. To determine who would have more difficulty with the surface tension of water, consider the Weber number. Weber number gives the relation between the inertial forces and the surface tension forces. K inertial, we have established a number of times, is equal to K rho times KL square into KV square. And the surface tension force, Kf sigma, is K sigma times KL, because surface tension force is sigma times the length. From this, we get the pi number, K sigma by KL divided by K rho, KL square, KV square, and which is 1 over KL. K sigma being the same water, K rho being 1. So we have this scale factor of 1 over 150. So the prototypes, which is Brogdinians, will have less difficulty with surface tension than would the Lilliputians. Similarly, the ratio of the viscous to inertial forces is like 1 over Reynolds number. And so K mu divided by K rho, K V, K L should be 1. So the two populations would have equal difficulty with the viscous forces. We had earlier shown that a flow past an infinite solid body having an elliptical cross section, the drag coefficient CD is a function of Reynolds number alone. We define drag coefficient as drag divided by 1/2 rho V naught square times the area. And this was a function of Reynolds number and geometry. 1/2 rho V naught square is like the characteristic pressure force times the area would give you a force. So drag divided by 1/2 rho V naught square times area. We have to select a characterizing area. And this, we make a plot. This is the typical behavior of sphere on a drag. For low Reynolds number, low means of the order of 10 up to about 10 raised to the power 4, the drag coefficient is a function of Reynolds number alone, nothing else. And at high Reynolds number, there is a difference between the drag experienced by rough spheres and by smooth spheres. We'll explain this difference in a later lecture. In fact, this is the difference that is used in many of the ball games that we play. In cricket, in golf. But the point to note here is that we have simplified. So instead of expressing the drag as a function of a number of independent parameters, we now write a drag coefficient as a function of one single number, Reynolds number, which is a group of parameters, a non-dimensional group of parameters, and the geometry. Can we do this for other situations? Let's apply it to the surface waves in a liquid. On a pond of water, in an ocean, the waves travel. The time period tau of the surface waves in water is found to depend on the density rho, the wavelength lambda, the depth h, gravity g, and the surface tension sigma. Rewrite the relationship in dimensionless form. So we see that the time period, the dependent parameter, is a function of 5 independent parameters: rho, lambda, h, g, and sigma. Can we obtain a simpler relationship in a dimensionless form? The list of independent parameters of the problem suggests that inertia, gravity, and surface tension forces are relevant for surface waves. Inertia must be there because density is important, gravity because G is important, surface tension because sigma is relevant. And we convert these forces into pi numbers. 3 forces, so we get 2 pi numbers as the ratios. Using the same process that we followed earlier, we write the scale factor for inertial forces. We write scale factor for gravity forces, mass times G. So Kf for gravity would be K rho KL cubed for mass and Kg. For surface tension, which is like sigma times L, Kf surface tension would be K surface tension times KL. From this, we get 2 similarity rules. K square V divided by KL Kg should be 1, and K sigma divided by K rho KL Kv square should be 1. And from this, we get 2 pi numbers. V square GL in the 2 flows, the model and the prototype, should have the same value, and sigma over rho L V square should have the same values in the 2 flows. The first one is recognized as the square of Froude number, and the second one is given the name Weber number. In fact, it is reciprocal of the quantity defined as Weber number. So, similarity requires that these 2 pi numbers must match. It is easy to see that either the wavelength lambda or the depth h can be used as the characterizing length. We choose lambda, the wave length of the waves, arbitrarily as the characterizing length. However, there is no physically relevant value for the characteristic velocity Vc or for the characteristic time Tc. So we will use this a little later. Here again, the normalized inertial force would somehow balance gravity force and the surface tension force. So the equation that we write for the phenomena would have a term inertial force on the left hand side, normalized. Then on the right hand side, we have normalized gravity force and the normalized surface tension force. The normalized gravity force would have G lambda by Vc square as its coefficient, and the normalized surface tension force would have sigma divided by rho Vc square divided by Lc as its coefficient. The first is recognized as 1 over Froude number squared, and the second is recognized as 1 over Weber number. Clearly, Froude number can neither be too large, for in that case the inertial force would be negligible, a non-admissible scenario, nor can it be too small, for then we would be neglecting the gravity effects altogether, and we know gravity effects cannot be neglected. Thus, the value of the Froude number should be of the order 1. Since Vc is yet unknown, we assert that the value of Vc should be such that it makes the Froude number of order 1. we set it arbitrarily equal to 1 and get Vc as under root GLC. And since LC has been taken as lambda, so the characteristic velocity is under root G lambda. If we use this as a characteristic velocity, then there would be only one parameter left, and that would be the Weber number. Once we know the value of Vc, we can obtain the value of the characteristic time, invoking pi Vc Tc over Lc as invariant, which permits us to use Tc is equal to Lc divided by Vc, which is lambda divided by under root G lambda or under root lambda by G. This is the characteristic time. And so the non-dimensional wave period, which should be of the form tau divided by the characteristic time, is now a function of Weber number alone and the geometry. Tau by tau c, the non-dimensional wave period, is a function of the characteristic Weber number and the geometry. The geometry of the surface wave is defined by the ratio lambda by h. So this is the final equation that we get for non-dimensional wave period. A much simpler expression than we began with. For deep sea waves, when h is very large, lambda is neglected. So the time period of the waves simply depends upon rho g lambda square by sigma, which is 1 over Weber number. We next introduce an alternative method of similitude, which is known as dimensional analysis. Most books in fluid mechanics deal only with dimensional analysis as a method of similitude. We believe that this is a method which is less powerful and is more difficult to use. That's why we have kept it for the end. The first known application of a technique similar to the present-day dimensional analysis was made by J.B.J. Fourier of the Fourier analysis fame in 1822. But the technique was first formalized in 1914 by E. Buckingham. The procedure assumes that the variables that control the physics of a phenomena can be formed into dimensionless groups. We would give here a kind of a recipe for carrying out a dimensional analysis. The recipe is rather simple, but the results that are obtained need to be interpreted carefully. The principal steps involved in determining the non-dimensional groups, which are the pi numbers that we've introduced earlier, are a list all the physical variables or parameters involved in the problem. Say x1, x2, xn, a total of n quantities, of which one and only one is a dependent quantity, a dependent variable or a dependent parameter, typically a dependent parameter, the rest being independent variables or parameters. Take, for example, the case of a pump, a water pump like we discussed earlier. The increase in pressure delta P is believed to depend on the diameter d of its impeller, the density rho of the fluid pump, the RPM n, and Q dot, the rate of volume pumped. So we can write delta P as a function of d rho n Q dot. Here the value of n is 5. There are 5 parameters involved. One of them, delta P, we treat as dependent parameter, and the other 4 are independent parameters. Choose a system of dimensions. For most fluid mechanics problem, a system based on mass, length, and time, MLT, is an appropriate system. Write the dimensions of all variables in the chosen system. Determine the minimum number R of the dimensions required to express these variables. For most problems in fluid mechanics, this number equals 3. That is, dimensions of all mass, length, and time are needed. So for R variables, of which delta P is dependent and the other 4 are independent, we write the dimensions of that. For Q dot, the dimensions are L cube T raised to the power minus 1. For diameter, obviously, is length. Density is mass into L minus 3. For RPM, it is minus 1 in time. And for delta P, it is M L minus 1 T minus 3. A fundamental theorem known as Buckingham Pi theorem states that the total number of non-dimensional groups of a parameter, which can be formed by combining the n physical parameters and variables of the problem, is equal to n minus r, where r is the number of primary dimensions required to express the dimensional formula of the n physical quantities. So we had 5 physical quantities, n is equal to 5 and r is equal to 3. So we can form 2 independent pi numbers out of these. Select a basic group of r independent variables or parameters. The selection is made such that all the dimensions involved in these r quantities and that non-dimensional groups cannot be formed from the products of the powers of those chosen variables. Let this be x1, x2, xr. In our example, let us choose d, rho, and n as the basic groups. The dimension of length are contained in d and rho. The dimension of mass are contained in only rho, and the dimension of time are contained only in n. All 3 dimensions are represented, and we cannot form a non-dimensional group out of these variables or parameters. It is now possible to form n minus r independent pi numbers out of these variables. Pi I is xi of the remaining variables, what we have not chosen as the fundamental parameters, into the first parameter raised to power a1, the second parameter raised to power a2, and so on. And the I varies from r plus 1 to n. We organize this in this table. We have chosen the basic group d, rho, and n. The other parameters are delta P, which is dependent, and Q dot, which is independent. We write the dimensions of this basic group. L is the dimension of D. ML raised to minus 3 is the dimension of density. T raised to minus 1 is the dimension of the RPM. Similarly for delta P and Q dot. We form a non-dimensional parameter as d raised to power a rho raised to power b, n raised to power c, and choose A, B, and C such that they match up with the dimensions of delta p and q dot. So we form two pi numbers. The first, we look at what we have formed with dependent parameters delta p. The power A, B, and C are found to be -2, -1, and -2. So that delta p divided by rho n square d square is a pi number. And the other with the independent parameter q dot, and the value of exponents are 0, -3, and -1. So that this comes out to q dot divided by n d cube. This is for the independent parameter and this for the dependent pi number. So we can say delta p divided by rho n square d square, the pressure developed by a pump, which is usually expressed in terms of the head h of the liquid, such that delta p is equal to rho gh. Using this, our non-dimensional dependent parameter becomes gh by n square d square, dependent parameter. And the independent parameter is q dot divided by n d cube. So there is only one dependent parameter and one independent parameter, so we can get one graph. For a pump, if we plot the head coefficient CH against the flow coefficient CQ dot, we get one single curve at all RPMs. The deviation at higher speeds is largely due to cavitation that takes place at higher speeds. And the higher the speeds, the cavitation takes place earlier. And that's why there is a performance deterioration due to cavitation. These curves separate out only because a new phenomena is introduced. As long as cavitation was not taking place, the only relevant independent parameter was the flow coefficient, q dot divided by n d cube. And so the head coefficient was a simple function of this, a line for all RPMs, independent of the RPM. Thank you.